All right, so in this lesson here, we are going to study about how we can calculate, how we can evaluate a double integral in polar coordinates. And so to begin with our journey right here, I have to mention one thing. So the entire lesson here is about a technique right here that we're doing double integral. But all of the philosophy and all of the fundamental understandings have all already been covered in the lessons prior to this one. Okay, and so I am going to now introduce a problem. So let's look at the following problem right here. And right now I call that a problem. And so we want to evaluate the double integral of the function 3x. So it's a function of two variables. We want to do a double integral over a general region. And so yes, using polar coordinates to evaluate a double integral over here is meant to be done on those general regions. So we have learned how we can calculate the double integral over a general region. But so here we're going to use a specific technique right here that's quite effective a lot of times in some of the general regions, in some of the non-rectangular regions right here. So this is the region I'm about to describe. So the region R, I am going to draw the picture instead of giving the wording, the worded description of that. We have two concentric circles of radius, of two different radius, and they're all centered at 0, 0. So all right, so the general region that we are calculating our integral over is this shaded area right here. So this shaded area is, you know, the area between an inner circle and an outer circle, and that's the area between them. And there are so many ways of writing the description of a region like this in using algebra right here. In one way, the most standard in rectangular coordinates. So if we're using completely rectangular coordinates, the usual rectangular coordinates, then we're writing the following. This set right here is a set of all. So the region R is a set of all x, y points, such that you see inside of this bigger circle. So the bigger circle here is radius 3, from the center 0, 0. Bigger circle. And then outside of the smaller circle, so there's an empty space right here, the non-shading part here. So that means it's x squared plus y squared being inside of the circle with radius 3. And so that's, make it 9 here. And then outside of the circle with radius 1. So it's going to be greater than or equal to 1. But then on the other hand, so that's the circle. But then if it's just simply this description, and we're looking at there's an inner circle and this outer circle. It's a complete going around shaded area right here. But that's not what we're looking at. Our real picture is only for the y value being positive, because we're looking at the area that's above the x-axis. So as another additional description right here, aside from this, we're looking at y greater than or equal to 0. That's one way of how we're describing this area, this shaded area. So clearly it is a non-rectangular region. Okay, and so the technique we're about to use here is called the polar coordinates, because so now with a problem like this, definitely we must have learned how to integrate a double integral, how to calculate a double integral over a general region, a non-rectangular region. But now if we apply that, so let me bring it over to the other board right here. Now if we apply that method, we've learned how we can, just the usual methods of how we learn how to calculate the double integral for a general region, for a non-rectangular region. Then we're going to have to break it up. Especially the area is going to be broken up as following. So the inner circle, that's the outer circle. So I can see this area as, so think about if we're placing the vertical stripes. It's a vertical stripes. Then so this vertical stripe here is being restricted between this vertical stripe where I put that is being restricted between, so that's y right here is being between, right? And we're gonna have to convert each one of these into a curve in terms of x. And so that's making it, the one on top here is the square root, right, of 9 minus x squared, and the one at the bottom here is the square root of 1 minus x squared. So that's y, but then this relationship is not really throughout the whole region. It's only, we have 2 points of breaking up right here. And so in here we have to switch to another inequality, because if we place the vertical stripes here, then we're going to look at y being less than or equal to the positive square root of 9 minus x squared, but greater than or equal to 0. And then if we're looking at a stripe here, a vertical stripe here in this region, we have a different setup trapping function, y greater than or equal to 0, but less than or equal to square root of 9 minus x squared again. So we have 2 different zones. There's a 2 outer zones here, and then there's the zone inside of that. And so it's a lot of breaking up right here for our work. And then of course the x value will go from, the x value is going to be even more challenging. X values is going from where? We going from here out, right, and from here in. So it's a lot of, so the stripes, we're talking about from -3 to 3, but then there's an empty area here. So x here is going from -3 to 3. So if we're putting all of this together, it's going to be a lot of challenge, right? It's going to create a lot of challenging issues for us to use the primary technique that we've learned in how to calculate double integral for a non-rectangular region. So we're going to change plan a little bit. The major thing about these inequalities is that we were attempting, the idea when we were doing the old methods is that we're using rectangular coordinates, where we are attempting to break these into rectangular subpartition. We're breaking our area, even though it's general region. The region itself is a non-rectangular, but in each of these subpartitions, we are trying to break it down as rectangular subpartitions. And that's the part that's making it hard for this particular region right here. It's very impossible to get it done. I'm not saying that we cannot do it at all, but really it's making it very challenging. So we change plan. And so we come to the following plan right here. The region itself, if you notice, it's looking as a region that's go around and around like this. So now I'm going to change plan. So I'm not even going to worry about mentioning about polar coordinates or whatsoever yet. But think about, we're going to divide, think of this as a sector right here. Then we can break this area into so many equal sectors. And each sector here, think about it, there's right here there's an angle amount, okay, and then there's an angle theta, okay, and there's so different theta values here, and then we're gonna break that into different radius. Okay, we're gonna break that into different radius length here. So the empty space is right here. Okay, so out here is the empty space, and so now I'm gonna put away these. Okay, so now see, we can call that, this is some delta 1. This is, some the theta 1, theta 2, theta 3, and then theta 4, theta 5. We break that into 5 different sub-equals. Theta 2. Okay, so these are all the equal changes. These are all the delta theta that we're looking at right here. And then this first level right here is R0. This is R1. This is R2. And this is R3 right here. And we break that down for now. We break that into 3 levels of subpartitions right there. All right. And so that's the idea that trigger up the use of polar coordinates right here. So now the way how I see each of these, they're no longer rectangular area, but there's still some kind of area, some subpartition, but being represented completely in the polar coordinates. So if I extract that, think about this, and then we can go this is right here. It's if we can extract a particular area out like that, then the picture is going to look like this. Okay. So in between some two theta, some theta I, and or I mean in some theta j to some theta j minus 1 to some theta j, we have some change between some radius I minus 1 to some radius I here. All right. So this is radius I minus 1, just like that. And then, so the area that I'm talking about here is transforming to this picture, is, I mean, in a more extracted and zoomed in picture like that. Okay. And so each of the areas here has a formula to calculate. And so the small little area there, we can call that it's a delta A, just as usual. Okay, and then see, I'm going to start going with the indices right here, the delta A, ij right here. So think about I is how, you know, the sublevels of radius. So the first level of radius change, the second level of radius change, and the third level of radius change, the going out level right here. So level 1, level 2, level 3. So here for this picture, I broke it down into the 3 levels of radius changes. And then here we got level 1, level 2, level 3, 4, 5, and 6 levels of the angle theta changes. So these are the sectors right here. So this is, so each one of these, we can call that each one of these right here, it's a delta theta. Okay, delta theta, and then some j, and then each one of these change right here. Each one of these change right here. Okay. In that picture, it's a delta R I. Okay, and so a delta A ij right here is going to be some change in the delta R sub I times delta theta sub j right there. Okay. But then this is actually not quite enough with the formula. So this is just the rectangular way, but the actual thing, if we think of that in terms of this picture, now I have to erase this because that's what I wrote it down is a common mistake to understand right here. We're close enough, but the real truth here is that, think about this picture right here. The actual area, it's a sector. It's a sector. That area here, it's a sector that comes out from the outer circle, because in polar coordinates everything is a circles in a radius from where the point is to the center. So we're looking at the area of a bigger sector here is going to be the radius I square multiplied with a change in delta. I mean change in theta. So change in theta j multiplied with I square. And then we multiply that with 1/2. That's the formula to calculate the area for any sector at some radius. So the radius here, the change in theta, okay, there's some change in theta. How much that change in theta we multiply with, so the area here, like a pizza slice right there, it's going to be R squared times delta theta times 1/2. That's the area for one little pizza slice like that. But now we're not getting the complete big pizza slice right here. We're getting just that part. So we're going to need to subtract the area of the inside one. My board is getting a little busy. And so I'm going to need to subtract, again, same formula, 1/2, but now R I minus 1 square times that delta theta j again, the difference between the two angles. Because now in terms of angles, this difference or that difference is going to be the same difference in angle, in the angle. So it's the same delta j, delta theta j. But then here is r square, ri square, and then here is ri minus 1 square. All right, and so the area here, that little small area that I'm extracting out to show the calculation, is indeed, yes, we can factor out the 1/2 delta theta j, and then what we have here is just the ri square minus the ri minus 1 square. And so with your algebra understanding at this point, we can easily rewrite this as a 1/2 times delta theta j times, now I'll go ri plus i minus 1 times I have to write that lower factor here, ri minus i minus 1. So this square, the difference of the two squares right here, it's turned into this factor product. And to make it easy for viewers, I'm going to rewrite this line right here. All right, so that's how we factor it. So let's put a pause on that right now. Let's come back to this picture. So the idea of an integral. Yes, we pick a, so now these are all the little subpartitions, just like in rectangular coordinates, but now we change plan. Instead of going with rectangular coordinates, we go with polar coordinates. So this is how we divide our subpartition. They're all round, they're all circular sectors, okay? But now in the end, we still need to pick a sample point. So our sample point right here is some point in each of these little subpartitions, some point. But now for this matter right here, when we're switching over to use polar coordinates, it's best that we pick a point exactly in the middle of the area. And the area itself is not a rectangular area, so it's a little hard. But the plan here is at that point right here, initially it adds some x star, some chosen x star at ij subpartition, and then at some y value star, right? Because any x in rectangular coordinates, any point is a point, and it's got x coordinates and y coordinates. So the x coordinate and y coordinates of this point right here is a chosen one, and we choose that in a way that it's right in the middle. And so now in polar coordinates, x star plus y, x star ij is the same as some, it belongs to some chosen r value in the ith sector, okay? In the ith sector, and then at some theta, chosen theta in the jth vector. Think about that point right here. It belongs to some chosen theta. That point is some chosen theta, and at some chosen theta, and at some chosen radius between these two. But then, as I said earlier, we purposely choose it in a way. That it stays exactly in the middle. So the more important part I see here is that means r star ith right here is going to be exactly 1/2 of. See, the length here is exactly. It's halfway between ri minus 1 and ri right here. And so it's exactly 1/2 times ri plus ri minus 1. This is the relationship right here. And so after this relationship right here, after explaining this relationship, we realize, so wait a minute, going back to this formula where we attempt to calculate the area of each of our partitions, subpartitions, then this part right here together with the 1/2 turns out to be just the chosen R value squared. And so the reduced version of this formula comes out being Ri star multiplied with, and now this here is the delta R, but delta Ri right here, and then this here is delta theta J. So this is now our simplified version of the delta A Ij right here. This is how we express the area. This is how we express the area of each of our subpartitions. The area of a subpartition at Ij positions. Okay, the I is the levels of radius going out, and the J is the level of the delta changes of theta changes going around. And so now, a little further into this, there's a relationship between these. So and now let me put away this rectangular description of our general region here. Just think about it this way. The function, some function, whatever function, it's a function in rectangular coordinates is a function of two variables x and y. So this integral right here, any double integral over a region, the way how we understand about it, the way how we used to understand about it, it's always it's a double Riemann sum for the function at chosen x value and y value in a partition. That's why I have the Ij component right here. Okay, and then multiply with some delta A Ij, and then we take the limits. The I is going from n, from 1 to n, and the j is going from 1 to m, but then we let the limits m and n both go to infinity. That's how we define an integral. And now even if we switch the integral, even if we plan to switch the integral over to using a double, using the polar coordinates convention, then it's still the same. Even if it's just a different style of expressing our subpartitions, but in the end it's still the delta A Ij multiplied with the function evaluate, because at that point when you evaluate into a function, you're going to have a height above that. So this is the floor, the x and y floor expressed in polar coordinates. Then that's the point, and substituting that point, that chosen point, into the function, you're going to have either a height above the floor or a height that sinks below this floor right here. So that's the x, the chosen x Ij and the chosen y Ij right at that point. But now when we switch over to using polar coordinates, this same formula right here can be understood as, okay, so the same problem right here, right, can be done as, yes, now think of that. Delta Ij here is already expressed in as the polar coordinates subpartitions. Then here, n going to infinity, m going to infinity. Okay, we got a double, but then we can rewrite this as the r star I, comma, the r, comma, the theta star j, and multiply with the delta A Ij. So now things look completely in polar coordinates. Now the version I'm writing here is a little is a cheating version actually. The real truth behind the scene is when you are converting from rectangular coordinates to polar coordinates, then every x value is related in polar coordinates by r times cosine theta. This is something that you've learned from your previous course. And then the y value is r times sine theta. And so the real truth of this, and I'm short of space, that's why I'm writing it like that, but the real truth of that is f of this part right here is supposed to be some ri star times cosine of theta star j, comma, and then this theta component right here, this other component, this y component after the comma is supposed to be some r star I times sine of theta star j. That's how it's supposed to write. But then in the end, the fancy r theta I cosine, r star I cosine of theta star j right here and comma and all that, it's a function of two variables, the r and theta. And that's why I can all reduce it down to a function f of two variables, theta and r like that. But in the end, this is the proper way of substituting it. All right. But now, going a little further, and now I really have to erase a picture right here. And I'm really gonna leave this line at the bottom here for a little while. And so, yes, a double integral from any of our general region, that any time that we now attempt to go with polar coordinates, then we can express that as the limits as n to infinity and m to infinity of the double Riemann sum, I from 1 to n, j from 1 to m, okay, and the function here, as I said in my cheating writing right here, then it's going to be some ri star, right, and comma some theta j star, okay, but then delta a ij. But then this delta a ij right here is indeed found to be this expression right here. So the revised version of this double Riemann sum, limits for n to infinity and m to infinity, okay, I from 1 to n and j from 1 to m for our function f of r or I star theta j star. Now multiply with, so the delta a ij right here is going to be r star I times some delta r I times delta theta j. So that's the complete double Riemann sum formula for that. But then, so in the end, so this is the way how we write the double integral in rectangular coordinates. But if we're looking at all of this right here, then if we're rewriting all of this in a double integral as a double integral again, but to be expressed in the polar coordinates, then here's how I'm seeing it. This Riemann sum here is the double integral over the region again, okay? But then the function here is a function of because think about it, when you're, and I erased my picture, but when we're getting the idea now, we keep breaking that into so many subpartitions. We keep breaking it more into the smaller delta theta and smaller delta theta, and also smaller delta r and smaller delta r. So just from a picture like that we've had earlier, now we want like a lot more. Okay, we want a lot more. And so that's why as we keep letting m and n go to infinity, then each one of these subpartitions gets so small to the point that there's no difference between the ri, the ri star and the ri delta anymore. And so that's why now in the complete integral version, this function now becomes this beginning function. So now I'm writing that in the complete form right here. The x here really is r times cosine theta. And the y value here can be substituted by r times sine theta. And then the dA right here, now in rectangular coordinates, it's dx, dy, or dy, dx. But now it's going to be r times dr d theta. And that's our final formula. And so this is the beginning of how we This is the technique how we turn our double integral from the rectangular coordinates to polar coordinates. Okay. All right. So now after some of the theory and some of the theoretical understanding, let's go back to the other board and restart the problem. So now I'll call that example 1. It was that same problem there, but now I call that example 1. We want to evaluate the exact same integral. The function is 3x, but then over the region, so now I'm going to draw the region. So that's the region. All right, so now that means using polar coordinates, I'm seeing the following. The double integral over this region R is the function 3x of the function 3x in respect to dA is the same as the double is the same as the double integral over the region where you're looking at 3 times, so now x is substituted by r cosine theta. So now it's r times cosine theta for x. And now the dA here is re-expressed as r times dr d theta. That's how we are re-expressing our double integral, but now completely in polar coordinates. All right, but now if we started to use polar coordinates, then we have to find a way to describe this region, the same region again, but we have to find a way to describe this region in polar coordinates instead of rectangular coordinates. So we're gonna stay away. That's why I also erased that description we've had earlier, because that description was in rectangular coordinates. We want to express the description of this shaded area, this general region in polar coordinates. So here's how I'm seeing it. In polar coordinates, it's just a matter about how much angle theta and how much radius. So this area here is indeed, at any point here, it's going to be at some theta, right? It's at any point in this area, it's going to be at some theta, some angle theta. And then the radius here is between 1 and 3, because this is radius of the circle. And so at any point that I express as radius and theta, that's how we express any point in polar coordinates. And I notice that it's always in between. It's always in between r is in between 1 and 3. See, any point here, the radius has to be between 1 for the inner circle and 3 is for the outer circle. So that's how I notice that. And then the angle here, the angle that makes from the x-axis, that's the way how polar coordinates is understood. Then the angle is always from between 0 to the complete side here is a pi. So the angle theta of any point in this region is limited to anywhere between 0 or anywhere from 0 to pi. So all of a sudden now we feel that we are ready. We have a complete description of our polar coordinates, of our general region in terms of the polar coordinates, and then we're ready to use this and turn our double integral into an iterated integral right here, an iterated double integral. All right. And so from that way, now the integral 3r times cosine theta times r dr d theta that we've had earlier, that same integral can be re-expressed. And by the way, this is an r squared, 3r squared, so we can re-express this as, see, we can go with r first, r going from 1 to 3, and it's a 3r squared times cosine theta dr d theta. And then as an iterated integral, we can integrate in terms of theta after from 0 to pi. All right, and so this is now a point that's being ready for us right here. We can rewrite this, so it's going to be 0 to pi, right, according to Fubini's theorem. And here we're looking at r cubed times cosine theta. Okay, evaluating this from 1 to 3, and then whatever the outcome will be, we are integrating that further in respect to theta. And so in the next step here, I'm looking at from 0 to pi, and that's making it 27 cosine theta minus cosine theta d theta after I substitute the 1 and the 3 into our current expression right here. And that makes it the integral from 0 to pi of 26 cosine theta d theta. And now the integral is completely ready. We are looking at 26 sine of theta and evaluating this from 0 to pi. And so the answer comes out 26 times sine of pi minus 26 times sine of 0. Okay, and the answer comes out all together being 0. All right, so now we have found the integral value for this double integral right from the beginning. So it started out as an integral written in the usual way, rectangular coordinates, which is the one that we're more natural with. But then because the region itself, like this, the region itself is making it challenge if we are proceeding this as in the usual way right here using rectangular coordinates. So we change our plan and using this, re-expressing this, breaking this down into subpartition as in terms of the polar coordinates, and then we were able to successfully come up with the final integral value. So let's have a picture of this to understand why it's a 0 right here. All right, so in my graphing space right here, the red axis is the x, green is the y-axis, and blue is the z-axis right here. So the function 3x, f of x comma y equals 3x is this function right here. It's a nice, it's a plane, right, going right through the y-axis here. All right, so now when we're looking at the picture right here, the part being shaded in this slightly purple color right here is indicating we want the surface, we want to integrate the surface over this general region right here, and that's how I'm seeing that from the floor. And so this is exactly matching with the description we've had. And so why is it being 0? Because, and now let me hide away the actual graph, and I only want to show the graph that stays on this, that belongs to the part in this general region right here. All right, so now let me turn the side view. All right, so now you can see that some part, thinking in terms of a net volume right here, then some part of the volume stays above the x-axis, stayed above the x and y floor right here. That's why it's some positive. But then there's some other amount of volume that stays exactly below. Okay, and that's the reason why if we are taking the net volume, it's all going to be a 0 volume. And that was the reason why our final integral came out with the results being 0. But again, using a volume here is just something to explain, to interpret the result of an integral. But an integral by itself it's not always a volume amount. All right, and so that's how we have used the double integral polar coordinates to solve a double integral over a general region. Okay, and so the major formula to understand at this point is that when you're starting out with an integral, with a double integral in rectangular coordinates, and if you desire to proceed with this double integral as a double integral in polar coordinates, then you do the following right here. It's the same region but then we're going to write the function here. So instead of x, it's going to be r cosine theta, and the y value is going to be substituted by r sine theta. And then the dA right here can be re-expressed as r times dr d theta. So that's the formula that we will be using for the rest of for any time that we're using polar coordinates to calculate a double integral over a general region. Okay. And then specifically in the case that we were looking just now, in the case right throughout problem 1 and example 1 that we're doing just now, then right now the region that we're doing right here, the region that we're doing as a description of the region, then we're looking at R, right, being, yes, the set of R, the set of all the points expressed in polar coordinates where r is between some two constant values, some r1 and r2. And then theta is also found to be exactly in between some theta 1 and theta 2. That's the case that the problem we just finished generally represent that case right here. That you have a region, right? You may have a region that r is going fixed. See, the distance r goes between some fixed r1 and some fixed r2 right here. Okay. R2, this is r1. So any point in that region stays between some r1 and r2, and then between some angle theta, okay, some theta 1 to theta 2. But these theta and r's, they are all constant values. And so in that way, if our region is recognized in this perfect expression like that, then the double integral in polar coordinates that we have already expressed, this double integral, according to Fubini's theorem, can be written as in one way. R from R1 to R2, and then we have the function or cosine theta or sine theta at R, and then we are integrating first in respect to R and then in respect to theta from theta 1 to theta 2. That's the way, and again, as I said, this is according to if we have already found, if we have already described, or we have a region that can be successfully described as changes between some fixed r to another fixed r and some fixed theta to another fixed theta value. Okay? And then according to Fubini's theorem, this is not the only way of writing our iterated integral. Here, we can also have another version, the same integral. It's all due to the nature of the region here being a region where r is changing between some fixed value to another fixed value, and then theta is also changing between some fixed value to another fixed value. So here we can go r1, r2 as the outer one, and theta 1, theta 2, okay, r cosine theta times r sine theta, and then r, but here we go d theta, dr. We can also do that. However, admittedly, a lot of times this one here is more popular. It's more common to use here, even though I'm saying that both ways is okay. All right. And now let's look at example 2. All right. And so this is another problem that we have. We want to evaluate this double integral. So right now in the beginning, it's always started out as a double integral in rectangular coordinates. But then the region here that we want to do, yes, it's a general region, a non-rectangular region. And then here it's a circle, but centered at somewhere off from the origin. So it's kind of like that. But now, being a circle or being whatever, it's not important. What I want you to see as a generality here is that this region here, yes, it's a general non-rectangular region, and furthermore, it's some kind of loop around, non-rectangular region right here, and it loops around. Okay, and so when we are handling a problem like this, again, if we are attempting to express r completely in terms of rectangular coordinates, yes, we may. As we can recognize that we can break it down as a one curve above right here. This curve, this upper dome right here is a picture of some y equals positive. See, the center of the circle is at 1, 0. So we're looking at, and its radius 1 here, of course, according to the picture. So it's 2 out here, is 0, 0 out there. Okay, I should have had that. And so that means from the center of the circle, it's radius 1 for that. So it's going to be 1 minus x minus 1 all squared in the parentheses. in the square root. And then the bottom picture here is going to be y equals the negative square root of 1 minus x minus 1 all squared. And then if we're doing our integral here, we can think about any stripe here as being limited between the lower curve and the upper curve. And for this problem here, we don't have to worry about the breaking up of the areas. But it's still, we're going to have to spend some effort breaking our curve into two separate curves, the upper curve, lower curve. And then integrating this vertical stripe can be placed starting at 0, see, x equals 0, and ending with x equals 1. Like that. Those are the vertical stripes. And so it's still somehow inconvenient with something like this. So let's see how we can use polar coordinates to do this double integral over this general region, being a nice round, being a nice loop around region like that. So this is the rectangular expression right here. We don't want to go there. Now, it's definitely important that you got to bring back your understanding about how you express a curve like this, a polar region, right? In a curve in polar coordinates. And so a picture like this, as a description, we're looking at the set of all points r comma theta. That's such that you see the angle, the radius r. When we study about polar coordinates before we arrive at this course here, then very commonly that r is expressed as well as some function. And this is the idea that we have seen from our previous courses. When we begin studying about polar coordinates, a lot of times the radius, see, always from the 0 over here, but the radius, because the radius changes depending on where we place our theta. See, when we reach some theta here, then it's a small radius. When we're at this theta 0 over here, we got some big radius. Okay? So radius is very commonly understood. It's very commonly seen that it's expressed as a function in terms of theta. And so here I see that my function of theta right here, for this particular round circle, I need to remind anyone, the radius changes between 0, changes from 0 to the function being 2 cosine theta, like that. So if anyone wonder how I got this right here, then you need to review your skill in the polar coordinates right there. And then from there, now the angle theta here, for this particular curve right here, to generate that, the theta rotates from 0 to pi. So here we're looking at theta changing from 0 to pi. All right. So this is the problem where it's unlike the earlier problem I brought up. Yes, theta does change between some two fixed values, but the radius is not. The radius is changing between some function of theta and between some function of theta and some other function of theta above it. So now to stay focused on this problem right here, we apply our experience we have learned from the integrating over a general region when it was still rectangular coordinates. Then the double integral. First of all, the function here is 4 minus x squared minus y squared dA. This double integral from the beginning can be rewritten as, first of all, the double integral over the region. The constant 4 is here, but x can be substituted by r times cosine. So here it becomes r squared times cosine squared theta. And then y is substituted by r times sine theta. So it's minus r squared times sine squared theta. And then here we have to, and the dA here is substituted by r times dr d theta. That's the first thing to substitute. But now after we have seen the description, of this region R over here, okay, where yes, theta is still changing between some two fixed values, but R is not. R is changing between some lower curve, R equals 0, to the upper curve, R equals 2 cosine theta. Okay, R is expressed as a function of theta. And so in that way, we apply our extension of the Fubini's theorem. Here's how I'm seeing it. Yes, just that similar idea. The only iterated integral that we can use this time. You see, the region was described previously. R is the the one that's changing from some function, some lower function to some higher function. So we have to integrate in respect to r first. So r here, the bottom point one is from 0 to cosine theta. And then with these things here, we can reorganize that a little bit. See, that all becomes minus r squared. Because if we're factoring out the minus r squared here, we're looking at cosine squared of theta plus sine squared of theta in that expression. Okay, and so all that here is a 1. That's how I become 4 minus, it becomes 4 minus r squared. But we got r times dr d theta. And now let me put away this extra writing right here. Okay, and then back to what I was saying in terms of setting up the iterated integral. So the first level, the first integral got to be done in terms of r, because r here, according to our region, r is changing from a lower curve of theta in terms to an upper curve in terms of theta. And then the next one here is to integrate in terms of theta. So we're going to integrate from 0 to pi. And that's how we're setting up. And this is the only iterated that can work for our case right here. Okay? And so now, when it gets to this point right here, yes, we can go ahead and integrate this. So integrating that in respect to r, and before we proceed, we can multiply that r to each term right there. Right? So now it's a 0 to pi, and now I'm looking at 2 r squared minus 1/4 or to the 4th power. All right, and we're evaluating this. We're evaluating this from 0 to 2 cosine theta. And then after that, we're going to integrate further in respect to theta. All right, and so in the next step, it will become an integral from 0 to pi. And then substituting these values in there, I'm going to end up with 8 cosine squared of theta minus 4 times cosine squared of theta. Okay. Theta. And now we have produced for ourselves a brand new integral completely in terms of theta. So now when it comes to this, you take your own, anyone viewing this lesson here is going to take your own route to come with the final work right here. Now in my work right here, I found the antiderivative of this. That came out being 5/2 theta plus a 5/2 sine theta cosine theta, and minus sine theta cosine cube theta. And we will evaluate this from 0 to pi. All right. And then yes, anyone learning from this lesson here can independently do the calculation on this using the fundamental theorem of calculus. And now this will come out being a 5 pi over 2 according to my calculation. All right. And so we found another integral over this, another integral, double integral over a general region. Let me now explain a little bit the meaning of this value right here. And again, an integral is not always a volume, but using a volume is the best place to describe this. All right, so here's our empty plane right here. And this is the picture. All right. And then I wanted to adjust the view a little bit. All right, so I have adjusted the view a little bit here. So now this is our graph of the function 4 minus x squared minus y squared. And now on the x and y floor, now I put in that equation. This is that equation right there over the general region. And so of course in the 3D perspective, it's not to see but on the down view, it's that nice circle right here. So now if I turn the view right here, then the integral outcome that we have calculated becomes the amount of space that's trapped inside of this. Okay, and you can see that the equation, the circle, when it's projected into the curve right here, becomes like a nice cylinder here, nice vertical vertically standing up cylinder, and then there's a volume between the cylinder here, inside the cylinder, and being restricted by that surface of our graph right here. So that is the meaning of this volume right here, of this integral, double integral right there. Okay, but again, it's just a way to explain what a double integral is for, but it's not always necessarily a volume right there, because here we know our function here is positive in that area, so that's why it's equal exactly that volume right there. Okay, but now what's the generality of what we have learned here? So as a generality of this example 2 that I brought up right here, yes, anytime that we're working with an integral, a double integral over a region, and initially written as a rectangular coordinates integral. And yes, in polar coordinates, we can turn that into a double integral over the region R of the function f of R cosine theta and R sine theta, and then R d theta. So that's the straightforward setup. But now, when our R here is described at the setup R theta satisfying when R is generally changing in between some g1 of theta to some g2 of theta. So R is no longer constant, but R is changing between some two functions of theta. And then theta itself is indeed changing in between some theta 1, theta 2, being constant. So this is the case that reflects our general problem that we have done in example 2 right there. So now in that case, this integral that we have set up right here forces us to use only one iterated integral. So we have to, according to Fubini's right here, the only iterated integral that we set up has to be the integral from g1 of theta to g2 of theta. And then the function here, yes, f of R cosine theta, comma R sine theta. And then R, we have to integrate in respect to R first. And then we integrate in respect to theta from theta 1 to theta 2. Right, so the integral that we've had here can all be done. The integral I can all be done like that, if I is the integral here. Right. And then this is the way how we're doing that. If we have this general description of our region in 2D space.